He then distinguished geoscience and he specializes in geochemistry and mineral exploration. His achievements include the Sky Young Scientist Award and Inspired Faculty Award for Earth Sciences. Dr. Y expertise covers advanced analytical methods including ICP-MS and isotopic studies, which is reflected in his published research work. His talk includes in-depth study of RE geochemistry, exploration techniques, and applications in diverse fields of geology. So, with this backdrop, I would now invite Dr. Parijat Roy for his speech.
Thank you very much, sir, for a nice introduction. And first of all, I would like to thank the organizer, and especially Dr. Alok, for giving me an opportunity to present what currently we are doing. And as this workshop is on various metals, strategic and critical metals. So, so far you have seen that we are all this. Can you hear now? So now, when the land deposits will be over, so where next we have to go? So that is the challenge. And so my topic is going. I'm going to discuss in brief the Indian initiative, what we are now doing for the deep sea exploration, and especially for this critical metal. So the outline of my talk will be that I will just give a brief introduction about the various non-living marine resources, and especially the polymetallic sulfide deposits, their occurrence and distribution, and Indian initiative, and the geology and exploration aspects which we are currently focusing on. So if you see, this is ocean floor. If you start this, if you can consider it as a coast, and then if you move towards the deep ocean, so there are various resources, mineral resources are available. So one is like manganese nodules. So they are polymetallic nodules, and then if you there are seamounts where we can get the FKM crust, and then we have in the mid-oceanic ridges where actually we get this polymetallic sulfides. So if you see, ocean floor is having a huge mineral resource, especially for these critical metals. In brief, if you see polymetallic nodules, so they are highly enriched in copper, cobalt, manganese, nickel, rare earth, molybdenum, tungsten. And how they form? They basically form in a nucleus, over the nucleus in an ocean bottom. So you can see it can be a sharp tail or anything, and then it involves both diagenetic processes as well as hydrogenic, means scavenging the elements from the ocean water and together with the buried sediments. So with time, these nodules actually, you can see this is the ocean floor diagram. We call them as a potato-looking material, and they are huge resources of cobalt and nickel and rare earths. Similarly, there is another which I have shown you is the cobalt crust. So the reason why there we are calling it as a manganese nodule because manganese concentration is very high. And in this cobalt crust, we get the very high cobalt concentration, especially more than 2% cobalt. So they are mostly forming over the seamount, just below the oxygen minimum zone in the ocean water, where you have ambient oxygen, and then the colloidal particles like hydroxides and hydroxides, they actually start scavenging the metals from the oceanic water, and then they start depositing on these flanks. So then you get these type of layers of crust. So So this is actually a hard strata, like basalt, and you get this dust over them, which is highly enriched in the metals. The third variety which I called you, the third is polymetallic sulfides. So they are basically enriched in copper, lead, zinc, gold, silver, and even many other metals. And they usually form in the mid-oceanic regions, where actually you have a heat source, and then I will again discuss this in my next slides, where actually the seawater basically percolates down, and then you have a magma chamber there. It got heated up, and then it started reaching the elements from the rocks, and then due to balancing, it come up again in the ocean, and then it precipitates, which give rise to, these are called black smokers. You can see these images, and then they give rise to these sulfides. So which are highly enriched in polymetallic sulfide. We call them as polymetallic sulfides. So basically now you understood properly that in ocean we have majority these three categories of deposits, which now we are exploring. So why we are exploring? Because most of these deposits are in the international water. So what is international water? Anything beyond your territory, that is exclusive economic zone, that is a range of 200 nautical miles. If you go beyond that, that becomes a international water. Now, international water is mainly ruled by the United Nations. So no man's it's nobody's thing. So what in United Nations there is a body called International Seabed Authority, which actually makes the rules regulations for the exploration in the international water. And currently, these are the three deposits for which a country can get exploration licenses. One is polymetallic nodule, cobalt-rich manganese crust, and polymetallic sulfide. And if you see, most of the countries in the world now have areas in the international water. So this is where India also thought that we should also enter into the international waters, because when the land resources will not be available, or when there will be a huge dependency of your natural resources for your own country, then we should have these deposits as a country's assets. So what if, though today there is no mining coal is available for exploiting these deposits, which is now on the table in the United Nations from 2022, that mining for providing a mining coal, but the current law says that we can explore these areas, and a country can get 15 years of exploration license. So if we are in future we are going to exploit it, then 50% of the resources will be countries and 50% will be for the mankind. That is the UN regulation. So with that aspect in mind, from India also actually ventured into the exploration of these deposits. Though India started this exploration way back in 1980s through National Institute of Oceanography for the polymetallic nodule. So this is the area where we have the polymetallic nodule for India, and then very recently in 2016 we took another area in the Indian Ocean for the polymetallic sulfide. So currently in my presentation also I am going to mostly talk on this polymetallic sulfide exploration, what Indian initiative we have taken. So as we know, ocean is a huge and it requires a lot of investment because we don't have the technologies, we don't have the proper infrastructure. So the first thing what India came forward with the deep ocean mission. So though we started this program way back in 2016, but in 2021 India launched the deep ocean mission with the major 6 components, and one of the major component is deep ocean survey and exploration. So with this objective, we moved ahead for exploring the deep sea for the polymetallic sulfide deposits. So apart from this, in the deep ocean mission, there is development of technologies. So we are very closely working with National Institute of Ocean Technology, Ministry of Earth Sciences, another autonomous institute like National Center for Polar and Ocean Research is a Ministry of Earth's organization. Similar way, there are development of ocean climate advisory services is going on, then energy from freshwater and advanced marine station for ocean balance. So I'm going to talk on this deep ocean survey and exploration because NCPR is the nodal agency, is the institute who has given the charge for exploring exclusively for this survey and for this deep sea minerals. So as I mentioned earlier that the story for deep sea exploration for India was not new. Almost this contract, India has signed the contract with the International Seabed Authority for 15 years, way back in 2022. And again further it is being extended because we have not yet reached to the exploitation stage. We are now making this mining technologies. The National Institute of Ocean Technology is making the mining technology. So now that contract has again extended beyond 5 years. So it is still there for 2027. And for the polymetallic sulfide, India signed a contract with International Seabed Authority in 2016, cabinet gave the approval, and then we signed the contract for exploration in 26 September 2016. So this is a particular area, you can say this is India, and this is a Northeast Triple Junction, and this is Central Indian Ridge, this is Southwest Indian Ridge. So we have a 10,000 square kilometer area for exploration divided into 100 blocks in this particular area. So every year, actually, we take the cruise from Mauritius. So Mauritius is nearby, and then we go and explore the things there. So as I was earlier also was telling that the water hydrothermal sulfides and how they form. So it's the same slide. And where they occur actually. So as I mentioned, hydrothermal sulfide is hydrothermal circulation where you require heat basically. So you can see that most of the mid-oceanic ridges of the world, all the mid-oceanic ridges of the world, you get this type of deposits. So 60% are almost at mid-oceanic ridges, and in that also 50% at slow and ultra-slow spreading, and also talk in that aspect. And currently there are almost active vents confirmed to 57, inferred to 84, but since last 1 decade, the exploration for this type of deposit has enormously increased. So these numbers are continuously changing, and if you want an updated data of this, you can always look into the inter-ridge database, where these vents are continuously being updated, where they are occurring and which are the locations. Now, when we talk about the metal concentration, as we know that these are hydrothermal processes, so your substrata geology plays a very vital role. So in the mid-oceanic ridges, what we expect that there are MORDs, mid-oceanic ridge basalts. But apart from mid-oceanic ridge basalts, there are a lot of ultramafics also get exposed due to the exhumation processes. So when we look into these hydrothermal processes, in you can see that in the ultramafic hosted mid-oceanic ridges, your percentage of copper is relatively high. But when we are in the basaltic domain, volcanics and all, somewhere you can get zinc concentration very high. Similarly, gold and silver also in the ultramafic hosted system, they are relatively high. But this also, as currently we are working on this, so actually we are unable to quantify every time that the same aspect ratio will be there. That if it's ultramafic, so definitely you will get high copper or so. It's not happening. So the reason probably behind is that the substrata, the hydrothermal fluid circulation, based on the substrate geology, if the faults and detachment faults are too deep, so then it can even interact with 2-3 types of substrata, and then your demobilization of metals can actually different, and then you get different type of concentration, though the process is similar like hydrothermal process. So as I was telling that if you see almost 65% is in mid-oceanic ridges, and also we know that there are some volcanic arcs that are basins wherever there is a volcanic activity, of volcanism happens, you can actually get this hydrothermal deposits. One more interesting fact which is now coming up is the deposits and the spreading rate of the ridges. So as I mentioned you that mid-oceanic, what is mid-oceanic ridge? Where actually the new crust is basically accumulating formed. So it's basically, if you have heard that it's a divergent plate margin, and in that divergent, when we talk about divergent plate margin, so they have different speed. So the divergent speed is not same. It depends on the magma which is available below the mid-oceanic ridges. So when we talk about slow spreading, there are three categories we actually classify them. One is fast spreading ridges, one is slow spreading ridges, one is intermediate ridges, and one is ultra slow spreading ridges. So what they are basically spreading rate per centimeter. So if you see, when they are less than 2 centimeter per year, we tell them or we say them as a ultra slow spreading ridges. And the occurrences of this hydrothermal sulfide now day by day we are seeing that they are mostly in this ultra slow spreading ridges. So what may be the reason? The reason is that since they are ultra slow, so the fractures, the deep detachment faults, they are actually forming in this region, and then the hydrothermal circulation actually gets a lot of time for circulation in those areas, and then which actually develops these type of deposits. So as I was just mentioning that why we should actually look into this mineral deposits in the deep sea. The reason if you see, so these are all in the left hand side are various percentage of copper from different mid-oceanic ridges with different setting, like ultramafic hosted, basalt hosted, then intercontinental rift arm basin, and then if you compare them with the land deposit, like we always consider them as volcanogenic acid sulfide deposits, so you can just see in what percentage the metals are. So these are huge deposits when compared if suppose land deposits tomorrow is not there or available or electrical technology comes for the deep sea. So then these are the huge resources for the mankind in the future. But what we need to search, so it's very difficult because you are actually having a water column of 3 to 4 kilometers. And then you are actually searching a deposit of 50 to 100 meters. So how to go for that? It's not so easy. So for that, what we are doing and how we have actually was able to identify the deposits. So on that, I will just now talk. So in detail, if I take you our exploration area, so this is India, this is Mauritius, this is our area. So we have divided our exploration blocks in 5 clusters, A, B, C, D, and E. So this is an ultra slow spreading ridge, that is Southwest Indian ridge. This is slow spreading ridge, this is Central Indian ridge. And we have almost 30 to 35 blocks of 10 by 10 square kilometer area in each of the area, and the total blocks, the total area is almost 10,000 square kilometer area. So you have to actually do the exploration in these blocks only, and you have to identify or find the deposits. So what is the major objective? So this is the major objective, to identify most potential sites of hydrothermal polymetallic sulfide mineralization in the application area, and then initiation of the associated scientific research. Because the scientific knowledge on the formation of these deposits is very less. Very few people, very few countries have worked on that. And this exploration and all those aspects have just started from 1977, 1980s. And due to the lack of resources and cost-effective things, so it made a lot of new developments every day we are seeing them, especially from the China or from the Americans and from the European countries, even Japan. So our main target is also to understand the genesis of these sulfide deposits as well as the association with the substrata geology. Together with, we have a very important component of baseline environmental studies because when you are in exploration, whether on land or whether you are on sea, this factor makes a huge thing, and as per the International Seabed Authority commitment, as long as we are doing exploration, we should have the baseline environmental data. So baseline environmental data is nothing. It's what the geology of that area, what the chemical chemistry of that area, what is the biological species available in that area. So all those actually covers in the baseline environmental studies. So one of the key things which I want to convey to the youngsters and everyone that if you are in an exploration program or for exploration for critical metals or minerals or any exploration, so now we cannot actually go ahead only with the geology or geochemistry like that. So multidisciplinary aspect is the key factor when you are going for big deposit search or exploration activity. So at NCPR, we have a team, dedicated team of not only geologists, we have geophysicists, we have chemists, we have chemical oceanographer, we have physical oceanographer, we have modelers, we have biologists. So everybody is actually working together just to look into the aspects, the key factors through which we can actually identify the deposits. So what main strategy we have actually adopted? Yes. Yeah. So first was the regional survey. So regional survey means it's a shipborne survey, which we are doing actually from the 4 kilometers above the sea floor in the ocean surface, and various type of studies like multi-beam bathymetry. Multi-beam bathymetry is basically to map the ocean floor. Then hydrographic surveys, which includes chemistry, physical oceanography. Then various geophysical survey. Then water sampling, which is one of the key factors. Then sediment and rock sampling, which is another key factor. So first initial 4 to 5 years, we actually concentrated on these aspects. The objective of these regional surveys is to narrow down our area. Basically, we did this survey in a 10,000 square kilometer area, and then we have to actually slowly narrow our points so that we can identify the exact location of these deposits. So once this survey is over, then we have to do the detailed and focus survey, which includes autonomous underwater vehicles. So these are very high technological equipment. They are like robots, autonomous underwater vehicle. You can just leave them from your ship. It will go in the bottom, work for 20, almost 42 hours, and then it will come back on the ocean surface. You can collect it and you can get the data which you want. And with this AUV system, you can put a lot of sensors like chemical sensors, physical sensors, geophysical sensors, and then you will get a very good image of the ocean bottom, which is of the resolution of 1 centimeter. From this, if you do the mapping of the ocean floor, it is almost 100 centimeter, 150 centimeter. It's 100 meter. So 100 meter is a very huge resolution when you are actually targeting for 50 meter objects. So this is where we actually further narrow down our exploration. So currently we have completed these surveys. Currently we have partially completed these surveys, and the next plan, which is we are planning in 2025, is the ROV video imagery and focus sample. That is, the locations which we will identify from these surveys will go ahead with the remotely operated vehicle. So these, like autonomous underwater vehicle, is like it is not tethered to the ship, but these will be tethered to the ship, but you are getting the live image of the ocean. So you can actually look into the ocean floor and you can actually collect the samples. They have the robotic arms. And also together with, we are planning for TV graph focus sampling, which will actually confirm that yes, there is a sunrise. So, as I mentioned, the first, once we have the, so I will now tell you in each step how we have actually done each of the studies, and then we actually plot them to identification. So, morphological features are the key factor because it then talks about your displacements, regional lineaments, and the OCC, ocean inflow complexes, because all these zones are the deeper zones. Deep zones means where there is a path for seawater to circulate. Seawater can circulate only through fractures which happens in the ocean floor. So these are the key areas where one has to actually focus. So we have actually systematically did the morphological features identification, which gave us an area that okay, they are the probable zones for fractures, and there is a probability that there will be circulations for the hydrothermal circulations. Then one of the key factors is the physical oceanographic studies. Because as I showed you the first image, if you can remember, I have shown an image of black smoker. That is a smoker from where you are seeing all the black material is coming out. So that material, what it can create in an ocean. So it can create a turbidity. Means if you are sending something denser material in ocean, water, it will create a turbidity. Similarly, what else it can create? Since it's a temperature system, so you can get a temperature anomaly also in the water body. So for that, you have to do the systematic CTD sampling. So through which actually we do the vertical cast, then we tow it, then do the dynamic hydrocast with different sensors. And what we used to get? So if you have some indicator that okay, there is a turbidity or there is a temperature, so you get such type of graph in the ocean. So you can just see at the depth of 2.6 kilometer, 2.8 kilometers, you are getting these anomalies. So once you get this anomaly, then our target starts to locate from where this anomaly is coming. So then we used to do the systematic mapping of that area, and then we try to identify the highest anomalies. So that gives us one target. Similarly, chemistry. So if you, when these hydrothermal fluids are actually coming out of the ocean, so they are highly enriched in helium, methane, then even carboisotope of methane and manganese concentrations. So what we do, we use wherever we got this such type of